This is the example that we left class with. We ended class. A thin metal plate occupies the region R in the first quadrant, bounded by y equals x and y equals x squared. The mass density measured in kilograms per square meter at the point xy is given by d of xy equals 1 plus x times y. Find the total mass of the plate, include units in your answer, and then find the average density of the plate. So we talked about how to find this region R, right? That's the region that we're integrating over. And each one of the points in this region has some kind of density associated with it. I mean, I could ask the question like, what is the mass density at the point 0.45? Be like right in here somewhere. Something like that. And you could just calculate that and figure it out. All right, so we want to find the total mass density of the plate, so we need to integrate. All right, so in class we decided that it really didn't matter which way that we wanted to slice it, this way or this way, and we decided to go ahead and slice it vertically. So that means we're finding our slices for some fixed x. Okay, so we'll have our outside integral, and this will be adding up all of our slices. So think of dx here as the thickness of your slice. And we're going to add up all the slices. That's why this has to go on the outside. So now how do we find the volume or area, I guess we'll say area of one slice, and then this will add the volume to it with the thickness there. We're going to integrate with respect to y, this inside part. Okay, so to find the area of this slice right here, we're going to let y go from x squared to x. The lower bound is x squared, and the upper bound is x. And then that'll give us a formula for the area of a slice. And then if we give that slice a thickness of dx, then we'll be able to add up all the slices from 0 to 1, and obviously the dx gets smaller and smaller. It goes to infinity, and we do the integral and the Riemann sum and all that good stuff. Okay, so let's go ahead and do this inner part, this inner integral from x squared to 1 plus xy dx. xy dy, sorry, xy dy. All right, so we're integrating with respect to y. So looking at this 1, I just have a constant. So the antiderivative of that would just be 1y plus, so now this is a constant times y, like 3y or something. So we raise the power to 2, and then we divide by a half. So we'd have 1/2 xy squared. And then we want to evaluate that from x squared to x. Okay, so the first thing we're going to do is remind ourselves that these we integrated with respect to y, so these are y bounds, which means that we're going to take this x and we're going to plug it in for y. And then we're going to take the x squared and plug it in for y. So if I take x and plug it in for y, I get x plus 1/2 x times x squared minus, okay, now I'm going to take x squared and plug that in for y. So that's going to give me x squared plus 1/2 x times the quantity x squared squared. And now we'll just simplify this. Minus, let's see, 1/2 x to the 5th. Okay, I think I'll probably just rearrange this and write it in descending order. I don't see any like terms here. Plus x. Okay. So that's going to give me the thickness, not the thickness, sorry, that's going to give me the area of one slice at any particular x. All right. Now, I want to give these slices some thickness so that I can find their volume and add up all my little slices. And now I want my pieces of bread here, my thickness, to get smaller and smaller and smaller and smaller and smaller, and keep adding up the individual volumes of these slices with dx getting thinner and thinner and thinner and thinner. And that's what this outside integral is going to do for me. And I'm going to let my slices go from 0 to 1. So now it's going to be adding up this slice with a thickness of dx, this slice with a thickness of dx, this slice, this, all the volumes of these little slices with a thickness of dx. Okay, so now we're going to do our outside integral from 0 to 1 of all this stuff with respect to x. So this now just becomes, we don't have a Calc 2 type problem. We don't have to worry about what variable or anything like that because everything's in terms of x. So you might want to pause the video and work it from here. I think what I'll do is just pause the video and work it out and then restart it where it's all done, so we're not wasting video time watching me write. All right, so there's that computation if you need to pause the video and write it, but that's how you get 5/24. I'd like to say something about the unit of measure here, kilograms. Let's go back up to the top and see if I have room to write this up here. So this integral right here, another way we could generalize that integral is to say that we did the double integral over the region. This is giving us our mass of our function, and then dA. Remember thinking about splitting this into these little tiny squares that we did like the first time that we talked about a rectangular region and the columns and stuff. So what is the unit of measurement for this piece? What's the unit of measurement for that piece? Right, that's your density measured in kilograms per square meter. All right, so that's kilograms per square meter. And then we're multiplying that by this tiny little area. This is like the height, right? This is like the height of your graph, and this is the area to get your volume of your column. This is the area of the base. That's the height to get those pillars. Okay, so the unit of measure for that is square meters. So we multiply that by square meters, and then you can see that the result of that would be in kilograms. All right, the next thing I want to do is just go through the example of slicing it the other direction. I think this would be good practice and show it comes out to be the same. So I'm going to set it up and then have you like pause the video and try it, or I'll just show all the computation at once just so you can see it, okay? So let's think about how we would set this up now. So now we're gonna do our slice this way. All right, so we're gonna fix some y. We're gonna look at some particular y value and try to figure out the area of the slice above or below, possibly, but in this case above because everything's positive. Here in this formula, all these are going to come out to be positive. X times y, we're in the first quadrant. So we'll have our surface above this, so we're going to find the area of the slice above that line. Okay, so that means we're going to fix this y here, and we're going to add up all those slices later, but so to find the area of that slice, then we're going to let x vary, right? Like from this x value here to this x value here. So this x value, oh, sorry, get that out of there. I was in office hours. Nobody came to see me, so it just ended. From this x value here over to this x value here. So here, x is going to be the same as y. So remember, when you're doing this x part, you have to put, this should be in terms of y. We said this generally when we had, whatever we said, g of y, h of y. All right, so you got to remember that to put it in terms of y. So then over here, the x value is going to be determined by, if we take the square root of both sides, and we'll just do the positive since we're in the first quadrant over here, the square root of y. Okay, so that'll give us a slice of 1 plus xy. And then we're going to add up all those slices from y equals 0 all the way up to y equals 1. All my slices will go up this way. Okay, so I'm going to pause the video and write out my computation for this red part, the inner integral, and then I'll start the video when I have it all written out. So if you want to practice, you should do the same. All right, how does that look? So just real quickly here, we're integrating with respect to x. So this is a constant. The antiderivative is going to be x. This is a constant times x, so I'm going to raise the power of x to 2 and then divide by 2. So I have 1/2 x squared, and then this constant of y is still there. Then I'm going to put square root y where the x's are. So here and here. All right, great. Then I'm going to put y where the x's are. So then I put y where the x's are, which is here and here. And then from there, I'm sure you guys are fine. Okay, so now we got to take all this business and put it up in here inside our outer integral from 0 to 1 dy. So let's do that. So we're going to have this guy from 0 to 1. dy. Okay, so I'm going to pause the video and work this out and then start it once I have it all done. And if you haven't done so, I'd encourage you to do the same. All right, so there we have it. Now, I have to share something with you because you didn't see all the behind the scenes. I was working this out and I got to this point. Let me erase. No, PowerPoint's being a pain, but I got to this point and I wasn't getting the right answer. I was getting something else over 24. And so I started all the way back up here like, oh, did I make a mistake? I went through like every single thing, you know, like you do. Did I add? Did I lose a negative? Did I copy something down wrong? All the way down. And my mistake was right here. I had an 8 over 24. Like the very last step. So I wanted to share that with you because a lot of times you see instructors like everything looks perfect. You know, then when they work stuff out, it's always wonderful. It's not. You know, I got down here and it was coming out negative because that was an 8. And I was like, oh, what did I do? So happens to all of us, but that's what we all do. We all just go back and look through every step and try to find the issue. All right, so hopefully that helps with this problem. The last part of the problem was to do the average density of the plate. So let's go ahead and take a look at that. So we have our formula for our average, and we've done a lot of the work here, but what we haven't done is find the area of R. We've already found this, which is 5/24 kilograms, right? Kilograms would be the unit there. So let's talk about how we're going to find the area of this region right here. Let me take this out. So now I'm going to draw a line again, but if you remember back from Calc 2, what you're basically doing is you're taking the area under the curve y equals x and subtracting out the area underneath y equals x squared. And that's going to tell you like this slice right here. So this slice, not with any volume, right? And when we were talking slices before, we were talking like there's something above it, like a big old slice of toast. That's not what's happening here. This is it. There's nothing above or below it. It's just this little stick, this little strip. And we're adding up these strips. And so the idea is that if I took all of the area underneath y equals x, so if I just did the integral from 0 to 1, that's pretty messy. If I did the integral from 0 to 1 of x dx, that would give me all this green area. Well, I don't want all that green area, right? I only want the little sliver part we're working on. So I need to subtract out this stuff here. I need to subtract out that. Well, what is that stuff? That stuff is the integral from 0 to 1 of the stuff that's underneath x squared dx. I can't make that color. Oh, it's not a very nice color. I got it by doing green and then covering it up with pink. All right, so that's the idea, and we can combine that into one integral. Not very attractive, is it? I can combine that into one integral using properties of integrals and say that I'm just finding x, the area from 0 to 1, x minus x squared dx. And so the x minus x squared like represents the height of each of these little sticks, not slices now, little sticks. Okay, so this is a pretty straightforward integration here. Nothing too tricky. Now watch me. When I say not too tricky and then I let my guard down, lose my concentration. All right, so that area is 5, 6, which kind of makes sense. Remember, this is area now, because the area of just this square is 1. No, that doesn't make any sense, does it? How about how about 2, 6, or let's see, 3, 6, take away 2, 6 would be 1, 6. That's interesting that I was like saying, okay, does that answer make sense? Because this whole area is 1, 5, 6 is a little big, isn't it? Let's try subtracting. How about 1, 6? Okay, that makes more sense. So now all we got to do is go back up here and let's erase this area and let's put in 1/6. And if we want to include our unit of measure, that would be square meters. So then we flip that 6 over and we're going to get, if we flip this 6 over here, the reciprocal of 1/6 is 6 times 5 is 30. So 30 over 24 kilograms per square meter, which reduces down to 5/4, 1.25 if you like, kilograms per square meter. All right, there we have it.